let's start. Good afternoon, and thank you for making up for this special seminar. Our speaker is Tabibat Sombon Banyakal. Tabibat was only able to make it today to visit Macquarie. He is on a big trip in Sydney. Will go to other universities as well. He's coming from Thailand. He graduated from MIT. And will be at Swinburne for the remaining time. He is around in Australia for 1 whole month, but most of the time with Swinburne, working on the JWST archival data. He works on galaxy clusters, mostly in the X-ray, and now looking into the other regimes. Today, he is not bringing us chips. He is talking about chips. So yeah, Tabibat, over to you.
Thank you for an introduction. So so my name is Tabiwat, and today I will present to you about a galaxy cluster with one of my favorite objects. Okay, so since I don't know too many background of the listener, so as soon as some people know a little bit about astronomy, but then people might not know too much about galaxy cluster. So for us, a galaxy cluster is a group of galaxies that are located together to form a disk giant. If you can see my mouse, a disk giant one object is actually one object. And the brightest cluster galaxy, we call it a BCG. It's basically the galaxy that are brightest and usually at the center of the galaxy cluster. If you find a BCG, you probably pretty much know where the center of the galaxy cluster is. And all these other galaxies here, we pretty much call them members. But we have to be careful because when you look at this image, for example, a lot of them are not a part of a galaxy. So like this blue spiral galaxy, all of these probably are foreground galaxies. And all these tiny dots in the back, smaller one, those are probably a background galaxy. So when I talk about a galaxy cluster, I only talk about the galaxies that have a similar color and similar color and shape, except the BCG that have a brighter or bigger. There are other interesting features of the galaxy cluster, including where this thing is called gravitational lensing. It's called strong gravitational lensing because you can actually use it to constrain the total mass of the galaxy cluster, including the dark matter, just by looking at the curvature of the strong lensings. And the strong lensing itself can also be used as a technique to study high redshift galaxies, because the galaxy that got lens have to be by definition behind the galaxy cluster. By looking at it, you can actually get some magnification on the brightness of the galaxies looking along the strong gravitational lenses. Okay, so that is basically the gist of what I want to talk about galaxy cluster. And let's talk about now. I want to talk about what is our understanding of a galaxy cluster and what is it going on from there. Okay, so let's say the first thing first is just like I showed you in the previous slide, almost all the member galaxies are red and dead ellipticals, which quench star formation. Not just all the member, but what we saw is the BCG or the brightest cluster in the brightest galaxy in the cluster is also red and dead, but especially really, really massive. So these are a typical property of almost all the members galaxy and the BCG inside almost every galaxy system. Another thing that we saw in every galaxy cluster is that it holds what called a hot intra-cluster medium, which is basically the gas in between the galaxies. So if you see the galaxy like this image, for example, if you look at it in the X-ray, the extended X-ray emission light will be extended all around. So that means there is a gas surrounding this entire galaxy cluster, forming this spherical shape. It doesn't have to be spherical all the time, but usually it is if it's relaxed. What does that mean? First thing first, it can only be seen mostly in X-ray. And from that, we know that the temperature of the gas have to be extremely hot, because only the very, very hot gas can radiate our energy in X-ray. If we convert it to temperature, the temperature of the hot gas is about 10 to the 7 Kelvin. So 10 million Kelvin hot gas. When I say hot, it's very, very hot. Okay, so here is the X-ray image of a galaxy cluster called 1835, Abel 1835 and redshift 0.25. Here is the image on the left-hand side, is the image in the X-ray. So you can see the yellow color here is where it's peakiest or the hottest or have the most density. And then here on the right-hand side is called the SC effect or Sanya Sodovich effect using the CMB and then the galaxy cluster acts as an object in front of the CMB and it casts shadow on the CMB. The signal of the shadow can tell you the property of the ICM too, but using millimeter wavelength instead of the X-ray. So these three images are come from the same galaxy cluster. From what I try to show is just looking at the optical image alone doesn't tell you the whole picture of what galaxy cluster is happening, because you cannot really see what the ICM is doing just by looking at the optical. And that's why the X-ray is important to actually understand what is happening inside the galaxy cluster with the BCG and all these member galaxies. Okay, so let's talk about what is our current understanding of the ICM and all the feedback about galaxy cluster. So here is a typical picture. We know that the BCG is especially very late and dead elliptical. That means there is no more star formation. The star doesn't form at all. That means what? That means the gas that is remember the blue here is a hot gas. So the hot gas here have to remain very hot. So, but when the X-ray hot gas radiate out energy, in theory, the temperature of the hot gas should cool down to lower and lower temperature. And eventually, when the temperature cool down to the center, then it should start to form new star and should make the BCG look like doesn't have to be a spiral, but it should be some high star formation inside the BCG of a typical galaxy cluster. But we do not see that. We see that the X-ray hot gas here remain very hot. It's 10 to the 7 Kelvin all the way from the past to the present. The temperature still seem pretty stable. And what does that mean? That means there has to be some mechanism to stop the gas cooling from happening. And what we call it agent feedback. Okay, so what is agent feedback? Agent feedback means the agent or the supermassive black hole inside the BCG or the center galaxy create this giant jet. So in this picture here, the blue is the X-ray and then the red is the radio. So you can see the radio create this powerful jet coming just from this tiny supermassive black hole inside the center galaxies. And this radio is so powerful that it go all the way outside the galaxy, go all the way into the ICM and create this cavity within the X-ray. So by just looking at the X-ray, we can see this darker patch of the ICM and we call that cavity or bubbles. And what does that mean? That means that the radio power just coming from the central galaxy of the BCG is powerful enough to create this cavity and in fact also heat up the gas and keep the gas from cooling, and meaning the star formation will be quenched at that particular region. Okay, so that is basically the idea or the general idea of what is going on inside a galaxy cluster. We have a galaxy cluster, a BCG, and an agent inside those BCG that have a lot of energy that are dumping up all the energy into the ICM, making the ICM remain hot and keep it hot for a long time. Okay, so here is a picture of a typical BCG of 100 cluster, more than 100 cluster. Each one of these is one BCG. You can see most of them are critically late and dead late and dead elliptical galaxies. Basically, all of them look like the same thing. It's basically late and dead and very elliptical shape, and most of them are very, very massive. So you can see the typical galaxy are much more massive compared to the member galaxies that are nearby. That means this BCG have a lot of time to start to grow into a bigger size by combining with other smaller galaxy merger. But all this merger doesn't actually create more gas because the merger is dry. So when it collides, just making it a much bigger galaxies. Okay, so why is it helpful? Because of the fact that almost all the galaxy clusters look the same is very important for cosmology. Because by looking at and then the reason it look the same is okay because first we have a very similar BCG. The cluster member look pretty much the same color everywhere. The metallicity of the ICM is pretty much the same thing. 0.3 solar metallicity pretty much everywhere. So here is oh sorry, I didn't show you. And then the gas fraction profile is also very similar. So basically, the amount of gas divided by the total mass is pretty much constant out the outskirt here. And it looks pretty much the same in almost every galaxy cluster. And the last one is almost all the BCG, basically pretty much every one of them have very low star formation rate. Typically about 1 solar mass per year is generally is the number of star formation of this BCG. By having all this property, we can pretty much use the number statistic to just start counting or mass function to start counting this number of galaxy cluster and try to constrain the cosmology just by looking at the galaxy cluster alone. Another thing that you can do is you can even use gas fraction profile here to help constrain the cosmology, including omega matter, sigma 8, and other parameters as well. So that is one cool thing about galaxy cluster that what we've been using for cosmology as well. Okay. So that was the beginning of why galaxy cluster is interesting and what we know so far or what we understand about it. But there's a but on the slide because I have to be a but coming. And the but is not all galaxy clusters look like that. In the past 10 to 15 years, we start to find a little bit more and more galaxy cluster that doesn't have a typical property. A lot of them have a large amount of star formation. Some of them have a giant AGN or giant quasar in the center. And some of these are shown here, including Abel 1835, RxJ 1532, and Max 1931. All these are massive BCG inside a galaxy cluster that have a ton of star formation. You can even see the O2 emission line, emission image from the above. Okay, but the three that I want to talk about today is called Phoenix cluster, H1821, and the last one is the one that I want to talk about the most with CHIPS. Okay, so for what is the Phoenix cluster? Phoenix cluster is the entire galaxy cluster with the BCG look like this. It's definitely not a red and dead elliptical galaxy. It's pretty much the opposite of that. As you start measure the star formation rate of these galaxies, it have 600 solar mass per year, or 600 times more star formation than a typical galaxy cluster. And the striking feature is this fragmentary structure that actually doesn't coming all the way inside the galaxy BCG, but it actually extends outside the BCG as well. So that what we think is happening is that it's actually the connection between the ICM, the hot gas, and the cold gas in the center. So the gas actually cool from the outskirts, and as it's cool and it's fall down to the center, and as the temperature go down from 10 to the 7, 10 to the 5, 10 to the 4, when it hit 10 to the 4, it get bright in optical. And it's go all the way down to 10 Kelvin or molecular cloud. In the center, you can also measure that. And then form a ton of new stars in the center. If you look at this object in the X-ray, you can see a very spherical shape or circular shape in the X-ray image with a very strong core in the center with the highest density located near this part. That means where the density is higher in the X-ray, that's where the star is forming the most. And when I say a spherical shape, it's mainly lacks ICM morphology, or it just pretty much look like a symmetric shape. Okay, Another one is H1821. This one is even more weird because the BCG is basically doesn't exist. The quasar or the AGN in the center is so bright that pretty much all the light coming just from this one AGN inside the BCG. With the radio emission is also very, very bright, not just the optical light. But people actually also try to find the star formation rate inside the host galaxy that by removing the light from the AGN, and you get star formation rate of about 120 solar mass per year. You from the brightness of the quasar, you can estimate the AGN accretion rate to about 40 solar mass per year. What does that mean? That means a ton of energy is already coming out in terms of the AGN feedback with the AGN accretion rate, but there's still so much gas left over that still form at about 120 solar mass per year. Okay, so these are two very different examples of what a BCG can be inside a galaxy cluster that not dead and late galaxies. Okay, so now it's time to talk about chips. Chip 1911, 4455. If another type of if another example of this kind of BCG. Okay, so here is chip 1911. The lead chip of the cluster is 0.485. Is discovered by the chip survey in 2021. I will show you the X-ray image soon. But the important thing is the BCG have also extremely high star formation rate at about 140 to 190 solar mass per year. Here is a Hubble image. You can also see a 30 kilosecond filamentary structure, just like the Phoenix cluster, and it extended on both sides of the galaxies, this side and also upside here. And it's in the optical, there is no sign of AGN. It's actually happening inside the optical spectra. Okay, and here is the data that I've been using to find this galaxy cluster called Pan star, and this BCG just look like a white blob. But by using the Hubble, we can actually resolve this white blob into the blue filamentary structure and the giant red elliptical galaxies. So that means this guy have basically two big components, with the red and dead elliptical galaxy and this blue filamentary structure. Okay, so here is the X-ray image. The X-ray image, when you see this image like this, the contour, this part here is where the density is the highest, or the part of the galaxy cluster that is the brightest in X-ray. Okay, and then typically what I show you previously, it looks like a circle shape, but this guy is not circular at all. It's furthest from circular, so we call it highly asymmetric on large scale. So this part here is much extended compared to this part, which have a kind of bunching up together. So what we think is happening is that two galaxy clusters are colliding. When it's colliding, or maybe one big cluster and one smaller cluster are colliding, then the hot gas inside this galaxy cluster are interacting with each other, and it push one on them to a side. And then that's why the shape of the ICM got pushed around, and then that's why it looks no longer symmetric. But the key important thing is in the optical, we see nothing. We don't see any merging or colliding of the ICM because what? Because the galaxy that are inside the galaxy cluster is having a lot of distance far apart from each other. So when two galaxy cluster colliding, it's basically going past each other, doesn't interact. So only in the ICM with the X-ray, we can actually see that this galaxy cluster is actually merging or colliding with each other. And then recently, so this data is 30 kilosecond of observation with Chandra, and yes, X-ray astronomy use kilosecond as a unit. But we got approved of 10 times that at 300 kilosecond of Chandra data to study this object, but that's still ongoing. Okay, so the first thing that we did after we get the X-ray data is try to get the morphology. So here is the morphology plot of all the galaxy cluster. Here is the peakiness and here is symmetry. So basically we want almost all the lilac cluster or the one that are circular and very peaky have to be on this top top right side. So it has to be very peaky and very symmetric. But our galaxy cluster is pretty much also the same peakiness with a typical lilac cluster, because this part here is also very dense, but it's not symmetric at all. It's actually one of the least symmetric objects we can find compared to a giant population up here. So that means this thing, just like I said, because of this asymmetry or disturbed cluster, we think what's happening is a major merger event. Okay, what else can we do with X-ray? We can get the density and temperature of each annulus center on the center of the galaxy cluster. We see that the density is pretty much peaky, just like a typical strong cool core cluster. But the temperature, you can see also that the temperature is going all the way down to the center. So here is the radius and here the temperature. So here the center part, we measure the temperature at about 3 keV, but at the outskirts it's all the way up to 8 to 9 keV. That means the hot gas itself is actually not that hot in the center compared to the outskirts. It's still 3 times 10 to the 7 Kelvin, but it's hot, it's cooler than the outskirts. So why we call this thing is also a cool core, because the part in the core is cooler compared to the outskirts. Okay, so from this information, we can combine them somehow, and then using this formula and get what called a pseudo entropy. What we try to measure is the heat content of the gas. So what is happening is we see that a typical galaxy cluster just go all the way like this, up and down, but it pretty much stop at about lovely 30 kilo keV centimeter square. But a Phoenix cluster that I showed you earlier and the CHIPS cluster is pretty much an example of object that can go all the way down to the center. That means the heat content of the gas inside the galaxy cluster near the center, that's where the heat content is the least. That means that the hot gas has been cooled down so much that the heat content is gone in the center, and that's why it leaves the entropy of the gas much lower in the center compared to the outskirts. And the core entropy is the lowest 10% of the other cluster, which we call accept, is a sample called accept cluster. And then, but the outer part is pretty much the same with every other cluster. So what we think is happening is that the gas inside the center of this cluster has been basically cool. And it's basically turned from really hot gas into some much cooler gas. Okay, so basically that's the paper. We see this merging galaxy cluster. We think what happening is a galaxy cluster is colliding. And when it colliding, the density peak of the ICM got pushed around. When it got pushed around, what happened is that the location of the AGN is stay still because the AGN is located at the center of the cluster with the BCG. But when the cold dense gas got pushed around a bit, that means the AGN is no longer have a same feedback efficiency to try to cool, to try to heat up the gas. And that's why the gas start to cool. And then that's why we see all these filamentary structure along the same axis with technically not exactly with the axis of merger. And we can see this peak, that there's two peaks in the X-ray, and this peak coincide with the node in the optical. So that means now is my hypothesis now is that the core or the cool core part of the galaxy cluster got pushed a little bit, and then that part of it get to start to cool, including the center part too, and it's all start to cool, and then that's why it leaves this big giant cooling in the center of the typical galaxy cluster. Okay, so that is basically the story what's going on so far. And then actually this year, there are two new studies of this object just coming up using completely different observation with different wavelength. So in submillimeter, we have Kasikani in 2025, and radio with this group just came out literally last month, sorry. Okay, so let me tell you what did we learn from this object, from these two wavelengths too. Okay, first, in submillimeter, we can do some measuring of the molecular gas. So we use NOEMA observation of CO221 at the same redshift with a resolution of about 15 kiloparsec. And you can detect this is a ton of, basically what this image show you is, basically we can calculate the brightness of this as the molecular gas mass or hydrogen 2. And the hydrogen 2 mass is 2 times 10 to the 11. Basically one of the largest files so far in almost all the BCG that have this much molecular gas in the center. What does that tell you? That tells you that the molecular gas is linking with the star formation. Because remember, the hot gas had to cool all the way down to molecular gas and then form star. So since we see star, we do expect to see some molecular gas. And since we see a lot of molecular gas, that means the molecular cloud here can support a lot more star formation. And what they claim they see is that they also see this extended part. And this extended part is the amount of gas is about 4% of all the mass of all of these molecular gas, sorry. And then this part here is what they think is really interesting, because they claim that this part here is coincide with the second knot that I showed you in the previous slide in the first study, that the blue filamentary structure of the top part here are coincide with this part. So what they think is happening is that this is a tidal tail of when there's a colliding or there's some activities moving around, then this molecular cloud is also moving with also some tidal tail coming out, just like what we see in Hubble. Another theory that can be happening is that because there are a lot of hot gas here with high density, the hot gas that could also cool down very fast and go all the way to molecular cloud in that region. But what I tell you, what does that tell you is that it either merger-driven tidal interaction or direct ICM cooling that actually create this large amount of molecular gas inside this galaxy cluster. Okay, and then the last study, let's see how much time I have. Okay, the last study that I want to show you about is radio, which is a very different wavelength compared to what I've been talking about for the past 30 minutes. This in radio, we basically can resolve many scales. The first one is we call it parsec scale HGN. So here, my figure is very small, but this white line here is 10 milliarc second. So the scale here is very small. Now we are looking not just the BCG, but just the HGN inside the BCG. And what they claim is that VLBA have so much high resolution that they can resolve a tiny jet inside the BCG, inside this HGN. So they think this is a tiny jet that are coming out. And what they think they see is that this thing also have this really weird shape in radio spectra. So typically in a radio spectrum, it should be power law, right? So power law should go all the way up like this. But this HGN here is actually have some turnover. And the turnover is happen at about 1 gigahertz, sorry. So we call this a GPS object or gigahertz peak spectrum. And what that tell you is when the HGN is very young, in this case it's only 1,000 years or 10,000 years, then the radio spectrum will turn over. And it's turn over at about 1 gigahertz, sorry. And that is a signature of a very young HGN. So what we think is happening here is what they are detecting very young HGN, or just the HGN is just getting started. Okay, and then apart from the parsec scale HGN, they're also looking at a kiloparsec scale or a little bit bigger scale using JVLA. And then, okay, they say, okay, this point source, this observation here, they basically say almost all the light is coming from the jet. Okay, because but the jet is so small, it doesn't resolve here, so it looks like a blob. But what they think they also saw is this. Do you see like this, like coming weird? They call it whisker. I don't know, they have a better name or not. But yeah, I'll just call it whisker for now. And then so they think these are actually real thing. That's actually a real thing. That's not a part of the jet. It's just a radio emission that coming from star formation now. Because this thing here is there's a there is overlap with this blue filamentary structure. What does that mean? That means they think the radio emission from the whisker is coming from star formation, because when you have a lot of star formation, you have a lot of supernovae. And the supernovae of this also create some synchrotron emission, which you can see in radio. And then from that whisker, if you remove the point source here and then calculate what is the expected star formation rate required for the for this whisker here to appear, is about 100 to 150 solar mass per year, which is pretty much consistent with what I found with optical spectra at 140 to 190 solar mass per year. So I think everything fit. Like there's a young jet, and then there's a whisker part, and then yeah. Okay, so what did the radio tell you? So what the radio study claim is that this BCG here is in the pre-feedback phase. The pre-feedback phase here means the agent is just about to start to turn on. The agent is super young. It doesn't have enough time or energy to heat up the gas to stop the cooling from happening, but it's coming. And that means the time scale is very different between how the gas quenching and then the star forming gas. So the hot gas from the ICM quenching and the star forming gas have a different time scale. That's why the two things doesn't basically match. So we see star formation, and we also see that the jet is about to turn on. And then the thing is, what happening is because the merger-driven turbulence coming in near the BCG, making the gas like mix up, have with a lot of high turbulence with cooling instability, and then that fuel the agent and thus restart the agent to about to get to a really strong feedback. So what we see here is a transition phase between no agent and have a ton of agent. Okay, so here I basically, okay, I think, okay, I try to finish it in 2 more slides. Okay, so what did we learn? We learned this object is a very unique object in couple cases. The first is it have a very strong cool core, yet it in the disturbed environment. So it means had to be some merging of the cluster. We learned that the BCG have a really high star formation rate, almost one of the highest BCG in redshift less than 1. And we learned from the radio that the agent feedback is just about to turn on with a very young agent with really small, like millisecond scale jet that have not affecting any ICM temperature yet. Okay, so how is that happen? We think what happened is there's a major merger between cluster making the ICM disturbed or asymmetric in some shape, displacing the cool core. And as it displaces the cool core, it allows runaway cooling to form a ton of star in a very short period of time, and also stop the agent heating from happening because the agent heating move a little bit off. And from that, could be turbulent, could be tidal interaction, could be direct SM condensation, fuel both the star formation and the agent that is just about to start turning on again. Okay, so why does it matter? This is my last slide now. Okay, I'm done. If you have questions, get ready. So basically, we know that at high redshift, there's a lot more BCG that have a high star formation, because at high redshift, the universe is very different. In the low redshift, most BCG is red and dead. At high redshift, a lot of them have a ton of star formation too. So we think this object will be like a transition phase, and we think we can use it to also help to understand what is the merger and the rapid cooling is happening inside the high redshift object. And also tell us a lot more about the cluster evolution from where the before the feedback start to where the quenching happening, and what happened in between is what this object show you. Okay, so my last sentence is that so this guy is starbursting garlic BCG with a strong cool core. That just happened to be in the transition phase between runaway cooling and agent feedback. Okay, and that's it, the talk.
Yes, Matt.
Yeah.
So I guess I didn't quite understand in the merging scenario that you have the cool core is displaced from the BCG, so that AGM feedback is switched off if there's no gas to feed the AGM. But the observations, it looks like the cool core is actually coincident with the BCG, and now you've got staff matching going on there. So is it just that it's a kind of timing coincidence that now the cool core is back with the BCG after having been displaced, or have I misunderstood?
So to be fair, we're not 100% sure whether the cool core actually got destroyed in the process. What thing happening is some part of the cool core get pushed out. So that's why a part of it is coming out, but I think the main part of it is still remain the same. But the fact that the agent stopped happening and about to happen again, we don't actually know why it stopped. I think it stopped happening just like you said, it's because of the cool gas. Not as much cool gas coming in, but as the star is forming and a lot of molecular cloud is coming in near there, then that part is make the agents restart back up again, and then that's why we see just the young agent inside. That we think is happening. Yeah, thank you.
Anyone else? I have one question because you were early on saying the red and early galaxies being the BCGs,
Yeah.
and later on you showed some different examples.
Yeah.
How it still goes in some common properties, why we are still seeing a variation, but there's might be some commonality.
Oh.
Early on, you also said metallicity, which is super solar.
Mhm.
Is it still the case for these ones or any other things?
You're talking about the difference between galaxy cluster with early galaxy and the galaxy cluster with our So actually, what we think, like for example, this guy,
Yes.
I mean, we don't. To be fair, we still think this thing is also an early galaxy. It's just that they have a ton of cooling that's happening on top of it. So we think the galaxy itself is still an early galaxy. But there is a ton of cooling coming from elsewhere. That's not coming from the galaxy.
Okay.
It's coming from the ICM itself. And how do we tell which one should have a typical early type galaxy or the one with a lot of star formation? We do not know, because we have very few objects that look like this so far, and we're still debating whether this thing is happening. So one idea is that the agent feedback that coming to heat up the gas when the galaxy cluster is very massive, it doesn't have enough agent feedback. So agent feedback have to saturate it at some point, and then after that, then the star can form. So like in that case, then we expect really massive cluster will have all these features. But then the problem is some of a really massive cluster doesn't have this feature. It's also an early type dead galaxy. So we're still not really sure. Yeah, that's still ongoing.
Yeah, I think that was what I was thinking about as you were going through your talk, is that at very low redshift. I mean, you call redshift a half low redshift.
Yeah.
But very low redshift, like local universe.
Oh, yeah.
Redshift 0.1,
Yeah.
we don't see anything like this.
No, yeah.
But that's where clusters have had long enough to relax and form their cool cores and the gas in the ICM to form
Okay.
cooling flows that go into the center of the galaxy. But we actually don't see anything like
Yeah.
this. In the unit. So kind of weird,
Yeah.
I think.
So is it, it has to do something with the evolution as you are going backward in time?
Right, but as you go backward in time, you expect these things to be more messy
Long.
mergers that
Okay.
relaxed. Cool. So that's why it's a little bit confusing.
So another thing is what happening is because in a very local universe there are very few clusters, and then that maybe this thing is like a very short period of time, and then that's why when we go to a higher redshift we have a bigger volume, and then that's why we see a little bit more of this. But yeah, it's really
So as you have shown some around, I think 111 cases or something, Are these the only one, or is it the one your group is working on?
Oh,
Are there
yes.
more known?
Oh, yeah. There are a
more
lot more known.
But they are not big in numbers, right?
Yeah. You mean the one that are star forming or the typical one?
Any BCGs?
The normal cluster, I think we on the order of 1,000 now.
Okay.
There's a lot of cluster, but a lot of it does not have a lot of information. It have like either SC effect to try to find cluster or the optical candidate, but yeah, it doesn't have a lot of confirmation of a lot of those. But yeah. But there are a lot of work coming up now to try to find, but most of them are right now, they try to find higher redshift object. Because we think higher redshift object are the one that will be more interesting, just like Matt said. There are more merging event and more star formation too, actually.
Mhm. Any other question? Comment?
With the last one that you had, with the merging groups, is there any evidence of the merger apart from the asymmetry in the X-ray output? Like, can you see
In the optical?
peculiar velocities of the galaxies themselves to see which belong to
Oh.
a separate cluster or anything like that? Is there?
We don't have any spectra data except that one long slit for the star formation rate. But yeah, having more velocity measurement of the sky would be very interesting.
Yeah.
Yeah, we don't have it. And it would be interesting to even see whether all these member galaxies have some different velocity compared to the BCG. Yeah, that would tell you a lot too.
And could the asymmetry be related to like the angle that we're seeing? Like if there are jets operating at a peculiar angle, and so that's what's giving the illusion of the asymmetry, or is the asymmetry?
You mean this asymmetry in the X-ray or the asymmetry in the radio? The asymmetry in the X-ray, we think it's real because the scale is really big. It's like this thing is like this one is 100 kiloparsec, so that is like 500 kiloparsec. But the jet itself, the one that they saw is very, very tiny, and yeah, I have not they haven't talked about whether the direction of that in related with the morphology of the X-ray.
Don't you have another BCG for the other velocity?
Oh, you mean for not for the cost?
I mean, if it's merging, there should.
Oh, yeah, yes, but we don't, we see just one BCG. So I mean, it could just be one massive cluster and one smaller one, and another one smaller one, the BCG just look like other member galaxy. And then, yeah, we cannot really tell from this image alone.
So you see asymmetries like this in nearby clusters on
Yeah.
very large scales, like megaparsec scales, because of more minor merger activity where you have sloshing
Oh.
gravitational perturbations that cause the gas to be offset
Mm.
and slosh back and forth.
So it doesn't have to be major much.
It could be your 300 kilosecond exposure might
Material.
show
Yeah.
sloshing type cold fronts in this.
Yes.
cluster.
Yeah.
30 kilosecond.
Yeah, definitely. I'm hoping to do more of that analysis, but 300 kilosecond is a lot and it takes me a long time to analyze. I'm usually used to doing only 30 kiloseconds. So. But yeah, definitely the new data coming in. Okay. This is very preliminary. I just started. We don't see two peak anymore. So in the 300 kilosecond of data, we just see one peak now. But this front is now it's even more obvious that it's the front. It could be, yeah. But
I'm guessing it is a cold front.
Yeah.
It's got some large scale sloshing. And any sort of secondary system is probably a much larger distance.
I see.
So when you're saying that the cluster, the interactions happened long ago and the second cluster's passed.
Yeah, right, yeah. And you get this oscillation of the gas in the center, in the gravitational potential.
Is there any way then to look at what's happened with the dark matter within that? Like, can you look at the lensing for it to see whether the center of the gravitation well is still centered in the middle of the cluster or not?
I think you can with weak lensing, yes, but I have not looked into that. But I thought the dark matter density peak should be pretty much located near the center of the cluster, right? Yeah, should not move too much.
And but if there's been a merger event.
I could, yeah, I could show it, yeah.
Depending on whether it's insurance.
So we thank
Yeah.
Kavivat again.
Thank you.